Hi, welcome to Practical Revit for Structural Engineer, Episode 4. This episode will focus on the modeling of the structural floor in Revit based on my experience in actual construction. The workflow I present in this video is the true workflow I used since the beginning of the structural design phase until construction completed. Please note that there are many possible ways to prepare the Revit model for structural engineering purposes. And workflow in this video is the one that fits my routine structural design work, giving the speed while offering acceptable accuracy. The simplest form of the structural floor is one-way slab behavior, such as a hollow core slab or metal deck. The structural behavior of a one-way slab could be described using these equations. Another form of the structural floor is two-way slab behavior. The two-way slab system could be in any shape, as there is virtually no limitation on its geometry. The two-way slab could be made from reinforced concrete, pre-stressed concrete, or structural steel. The structural behavior of a two-way slab could be described using these equations. You can create a structural floor model in Revit from the menu, Structure, then Floor. When you already create a floor element, make sure that the structural and the enable analytical model have been checked. After the enable analytical model has been checked, this will enable Revit to create a finite element for the floor. The finite element for a floor could be seen by setting the visibility option as shown here. Now label the Revit type in order to be used for schedule filtering during quantities takeoff. Choose whatever name you like. It could be RC flat slab, PT flat slab, RC beam slab, precast slab, whatever. Then from the structural material option, create the physical material property that matches the material you are using. To control the node of the floor element, the height offset from level parameter should only be the thickness of the floor finishing in the main Revit model. It is highly recommended that the height offset from level parameter shall be set to 0 just before transitioning the Revit model to finite element software. This way, the problem of unintended unconnected nodes will be eliminated. The structural floor could also be inclined, slope, or ramp. You can modify the flat floor into inclined by choosing the Modify menu, then Edit Boundary Mode. Create a slope arrow direction and adjust the slope as required. It is common to have floor depressions such as a balcony, bathroom, and corridor. Basically, there are two methods to create floor depression. Method 1, create a separate floor element with different thicknesses. For structural analysis, this method offers high accuracy if done properly because of the structural analysis performed based on the actual thickness of the structural floor. However, this method is not suitable for depression with a curved shape because of the risk of the unintended unconnected node along the curved interface. Remember that the curved you see in Revit might not be the exact same curved after transitioned into the finite element model, hence, the curve that looks perfectly aligned in Revit might not guarantee to be aligned in the finite element model. Method 2, create void and cut the base geometry in order to form floor depression. Since void also creates opening inside the shell element, therefore, all those voids shall be deleted in the pre-finite element Revit model before transitioning to the final finite element model. The advantage of this method is there is no limitation on the shape of depression. And the shape or depth of depression could be changed as frequently as we want according to structural and architectural coordination during the design phase. The downside of this method is the structural analysis is based on the thickness of base material and neglects the void part. For the slab thickness equal to or higher than 200 mm, and depression depth between 30 mm to 50 mm, neglecting depression is most of the time considered acceptable in practice for the structural analysis part. But for the structural design part, the effective depth should still consider the actual depth, which is the reduced effective depth due to the presence of depression. You can create a void by choosing component, then model in place. Now create void using void extrusion method, then cut the void from base geometry in order the obtain floor depression. Again, such void also creates opening inside the shell element. At this point, always name your void systematically, so that those could be easily deleted all at once later on in the pre-finite element Revit model. There can be several floor levels. The mistake that structural engineers often made is using the height offset from level parameter in order to represent different floor levels. This is the major cause of unintended unconnected nodes in the finite element model later on. Always create specific levels for each unique floor level and only use the height offset from level parameter for the sole purpose of floor finishing thickness. Unlike the structural column and the structural wall, most of the time an automatic node merging is not required for the structural floor. Just make sure there is no other element but the structural floor in the pre-finite element REVIT model. This is to prevent REVIT from trigger the auto node merging unintended. For the pre-stressed concrete floor, currently, I personally did not have success with transitioning tendon models in REVIT into finite element model. Therefore, what I do at the moment is creating a tendon model directly in the finite element model. Whenever the columns or walls located outside each other, then the transfer beam is required. The modeling of the transfer beam could be in the form of a structural floor as shown here. Modeling transfer beam using shell element is superior to using line element, especially when the two ways eccentricity required. In general, there are two types of foundation: with and without pile. The foundation without pile or the pile cap could also be transferred into finite element model using the structural floor. Option 1 is modeling the foundation using the structural foundation category in REVIT, and replicate the foundation geometry using the structural floor when transitioning into finite element model. Option 2 is modeling the foundation using the structural floor in REVIT right away. The process of transitioning the foundation in REVIT into the finite element model is now identical to how you do with the structural floor. In summary, the workflow to export the REVIT model to the finite element. First, you have the main REVIT model that everything modeled as per actual. The floor can contain offset and depression as per actual. Then, just before exporting, you save as your main model to the pre-finite element REVIT model. Here, you reset all floor offset to 0 in order to eliminate the unconnected node problem, and delete all void cut if any. Finally, you now have a proper finite element model for all of the structural floor. According to the workflow from the previous episodes for structural walls and structural columns. At this point, we now have a complete picture of pre-finite element REVIT model. Each pre-finite element REVIT model shall contain only the related structural part. For example, pre-finite element REVIT model for structural column shall contain only structural column. Any element other than the structural column shall be deleted. The exception is the structural floor and shaft opening could stay together. Now, all pre-finite element REVIT model is ready to be exported to your structural analysis software of choice. If you follow the guidelines explained throughout this video series, you can now able to control the structural behavior of the finite element model that exported from REVIT model for the whole building. Congratulations! In case you are seeking to further model the foundation with piles. The next episode will include the process of how to obtain pile coordinates from REVIT model. So stay tuned.